What I'm going to do is try and spend a few minutes convincing you that this is important, and by this I mean the topic of trying to make sure that the software that embodies research is treated as a high-quality software output and not just kind of a throwaway thing, and then to talk about some of the things that I think are important in achieving that. Now, in terms of the content, this is kind of taken from a 30-hour lecture course that I do in UCL on this topic, and obviously we've only got 3 hours today. But I didn't know what level people are at, and so it was very hard to decide which bits to pull out of that for today without having a conversation with you. So what I want to do, I'll do the intro first, then I want us to have a conversation and just try to gauge which bits would be boring for you to be told again and which bits will be interesting, and we'll try and compromise about that and then pull out some material from that lecture course that will be most valuable today. But the other thing from that is just to give you an index of the kind of different topics that are in that, because all the lecture notes are online. All the lecture notes are online under a Creative Commons CC BY license, so if anybody else wants to run a lecture course in software engineering for researchers, then feel free to borrow the lecture notes. Well, let's start with the sort of motivational stuff. So as I said at the beginning, I'm not sure about I basically work at UCL and at the Turing Institute to work with researchers to try to help make the software that comes out of research, I usually say, have a standard of correctness better than, oh, the graph looks about right, and be usable by somebody other than the PhD student or postdoc who wrote it, right? Which is a challenge for much of the software that comes out of the research community, and I think that's really important. So you may have heard this old saw garbage in, garbage out as being the thing about computing, right? If a computer program gets nonsense in, it gets nonsense out. That's not our problem, right? Our problem in computing with maths in the broader sense, computing that's going to make a graph or some kind of number at the end, right, is what I call the Cyro problem, sensible in, reasonable out. This is what I mean by, oh, the graph looks about right, okay? How do we know that the maths we've typed in is the maths we think we wanted to type, maths we think we've typed in is the maths we wanted to type in, right? And techniques to do that are, I think, at the heart of the challenge of software engineering for research. I'm going to talk about some of the kind of failure modes that we see around in the research community around software, and hope that we... Now, this is not me being mean, right? Because I have done all of these things, right? So I have perpetrated every bad practice that I'm about to talk about. Really, I'm just introducing this to try and set the scene of the nature of academic software and why I think it should be different. So one of the things we do is we never look until to see if anyone's done something before. Right? There is a lot of awesome libraries out there, but we all pride ourselves on being super clever and therefore think, oh, well, I'll just write my own one. It's great to write your own one so you understand how the algorithm works, but then, for heaven's sake, throw it away and use one of the ones from the standard library toolbox, right? Use one of the ones from somewhere on the internet, please. But people often then code until it works, generate a figure, and throw the code away. This annoys me, but it annoys the research councils more. Right? Because the research councils keep paying for awesome PhDs, and the code disappears at the end of it and isn't built on by the next generation of scientists. That sucks. Please stop it. OK, so that's one kind of problem that happens. And then there's the code which, it doesn't have to be in Fortran, but it often is. And it's really not been engineered for readability. Right? It's been designed to get some results, and often, honestly, it's been designed to make the person who coded it feel as clever as possible, right? If you've ever written some code and gone, that was awesome, I just coded like Bob's algorithm in 7 characters. I am the super cleverest coder in the history of computing, right? That's terrible. Don't do that anymore, ever. The purpose of one of the opinions I'll spend a lot of time banging on about today is that, for me, code is the only rigorous and reliable way of communicating an algorithm. I hate, the kind of pseudocode you see in research papers is all very well, but a well-written actual library that's readable, proper R or Python or whatever, is the best form of scholarly communication about code. So let's engineer for readability and not try to make ourselves feel really clever. One of the things that many people will recognize is the experience of somebody saying, well, we've got this nice piece of code, and I'd just like to add one feature to it, please. And everyone goes, great, but we have no tests, so the only reason we believe in the outcomes of this, believe in the outputs of this code is the sort of accreted trust over several years of use of it. And if you start fiddling with it, we won't know whether it's reliable anymore. So then people go off and write another one, right? Well-structured code is extensible and drives against that phenomenon of everything being thrown away. Then there's a wonderful solution. People say, right, I know how to fix this. Clearly, academics are terrible at writing code. We're not, right? We're just busy and have all the metrics. Clearly, academics are terrible at writing code, they say. Let's hire in some proper software engineers from outside to come and do it. And what you get is enterprise engineering with more UML than you can possibly imagine, and something which is not very relevant to the research context and is unmaintainable by researchers. So that's another failure mode you will see. Then there's another failure mode, and I've perpetrated this one a fair amount, which is, right, so let's make a tool to solve the general problem, designing a system to pass arbitrary condiments, to quote the famous XKCD cartoon. And it gets a computer science paper in some e-science conference and is never used by any researchers to actually do any real analysis. And I've perpetrated this one a lot. So let's try not to do those things. And then finally, and this is another one that annoys me, is the fetishization of performance, right? So anyone who owns a supercomputer will get really cross with you for not hyper-optimizing your code to be just perfect and make the absolute most use out of that machine whatsoever. This is massively a waste of time, in my opinion, because it selects against readability, it selects against maintainability, and it selects against adaptability. It selects against the ability to add new thing. You optimize it for a particular architecture. That computer will be thrown away very soon. And you get to publish a graph of performance, and that's about it. So these are some failure modes in scientific software which I don't like. And I would prefer to see things done differently. So let me just continue with my introductory ranting. And make a few more points from the lecture notes. Zoomy in, zoomy in, zoomy in. So I'll be using Python for the examples today in this course. So this is not a course about, the big course is not a course about Python, it's a course about software engineering, but I have to teach using the medium some language for representation. But there's just one other point I wanted to make that wasn't on the previous set of slides, which is this one, which is if I'm doing some repetitive task, right, and I want to make that into a script, I'm doing some analysis, people say, right, people will often say we do that for labor saving, right? But that's not the reason I believe in automating your entire research pipeline from the data to the conclusion as a script. Yes, it does save you time, but it creates something that makes it reproducible, right? If you are manually messing around in Excel, I have no way when I see your conclusions of verifying that your conclusion is reliable. But if you have a script, some code in R or Python and Jupyter Notebook or wherever, which describes your research pipeline from the raw data to the final figure, and I can run that again, then your work has become auditable, right? And audit for research, reproducibility, is extremely important, particularly where, for more and more of the work we're interested in data science, our conclusions are going to be political footballs, right? They are going to be something where people will challenge. And the reason I got into all this stuff, I used to work in climate modeling, and some of the stuff that went wrong there in the sort of late noughties, in terms of some of the modeling tools that we had, there were only minor problems, but they were very significant in terms of the public trust in the scientific process over that. And so it's really, really important that if we're going to make conclusions from sophisticated analyses that we make them auditable, right? Which for me is a stronger challenge than reproducibility. And software engineering is the key to that, right? Because by making our analyses scripts, the whole thing into something which can be rerun and the analysis come again, then we get around those problems. So that's kind of my introductory sort of pitch on why I think software engineering for research is like extremely important. Now we need to decide what we're going to do, what we're going to try and look at in terms of today in terms of particular techniques and things that I think are important to achieve that. So what I wanted to do is really just get a survey. So first of all, who here writes computer programs? Okay, that's good. Who here ever writes computer programs in Python? Okay. Who here ever writes computer programs in R? Okay, interesting. Thank you. Who here ever writes computer programs in compiled languages like C or C++ or Fortran? Okay, fewer. So Python was the right choice to use as the medium of communication on the basis of that survey, which is good. Fine. In terms of your Python, how many people write object-oriented Python with classes? Okay, good. How many people have taken their Python code and turned it into a library and such that it can be installed by somebody else with pip install? 2. Great. That sets the level brilliantly. Fine. Next question. How many people are using Git version control? Great. How many people are using Git version control and occasionally create new branches to do work on? Less. How many people are collaborating with others through Git using pull request, what they call GitHub flow? Much less. Okay, so that sets the level for that bit. Good. Fine. In terms of programming techniques, who would be comfortable with writing code where one function took another function as one of its input parameters? About half. Okay. Who would be comfortable using what we call generator methods in Python? So the yield statement and that kind of thing. Fewer. Okay, fine. Who's done? Who knows how the details of how? Right. Okay. Let me draw this. If I write a NumPy expression with A is of shape 1, 3, 3, and B is of shape, so it's a 3D matrix with shape 1 on its first and size 3 on its second, and B is a 3D matrix of shape 4, 3, 1. How many people would know what shape A plus B comes out as? Okay, that 1. Brilliant. So that sets some useful stuff to do. Okay, good. So I will now, so therefore, we are going to do Python packaging. So how to take your code and bundle it up into into something that you can stick on PyPy and publish it. We're going to do GitHub flow. Did somebody say that again? I hope that. Okay, we're going to do GitHub flow. That is how to work collaboratively with a large number of other people on an open source project through pull request models. And we're going to look in more detail at efficient Python programming with NumPy, with numerical Python. Okay, so we'll sort of do. We've got 3 hours, so we'll sort of do an hour on each of those, and that will be kind of a selection of content from the material. If we do those 3 sections, how many people are like thinking, well, I know all of that, I should go, this is boring? How many people are thinking, oh my God, I won't be able to address these topics because I need to learn Python first? Okay, good. I think we've sorted out some useful content for our 3 hours. Whew. Okay, that's good. So let's look at Oh, another topic that's important. Sorry, I forgot to. That's really important. I should have added that to the list as well. See if we can squeeze one more in. Right. How many people, when you're writing code, write unit tests? Oh, that's not enough. We need to do testing as well. I will try and squeeze testing in as well, but shout at me if we're going too fast. Okay, I need you guys to help set the pace as well. Yeah, all right. Let's do software projects. Let me switch to the notebook version. So how many people use Jupyter Notebook? Yeah, right, that's everyone. Cool. Okay, so first of all, how many people have ever written Python that didn't use outside the Jupyter Notebook, just using an editor? So fewer, that's usually the case. So just to make it clear, if you want to turn your code into libraries, right, the first thing you're doing is the process of taking a notebook and looking at the code in it and thinking about how to turn that into some code that can be used as a library or as a standalone tool. Okay, so that's what we're going to look at now. So first of all, what you need to know is that you'll want to use an editor. So I use Atom for that. I'm working in the notebook for the purpose of these lecture notes, but one of the things you'll want to do that, so let me just find where we drop into this. So the example code I'm using there comes from earlier in the course where we are never mind. I'll skip over. Anyway, so we've got some code in this example which is building a little house, right? So it's building an object for a maze. So you've got different rooms. You can go north from the living room to get to the bedroom and that kind of thing, like an old choose your own adventure stuff, right? So imagine that's already been written, and that's just been written in a notebook. And what you want to do is turn it into files. Okay, so you're going to take your code and so let's build up the package structure. So in your project, your root directory on GitHub, you will need to have a folder which will be the name of the Python package you want the Python package to have. So here I'm going to call it maze tool. And in that folder, we're going to have a file called here maze.py, which by tradition has the same name as the name of the class that is defined in that file. So here the next object is a room in the maze, and it has a file name room.py, and that class is defined in there. Okay, so there's this correspondence between one class per file, with the name of the file being the name of the class. So don't have all of your code in one big module. Then you need to tell Python that this is going to be a Python package. And the way you do that is by putting an empty file called __init__.py in the folder, and that tells it that this is going to be a Python package. Okay? And that's how you magically bless a folder to turn it into being a Python package. And once you've done that, so let's just start running this notebook. You can now import it, and then it exists. Let's skip that content. So another thing we'll want to do when we take our tool and publish it as an independent tool is we'll want to be able to write a command line interface, right? We want to be able to make it so that it can be invoked from the shell. And the library for doing that in Python is called argparse. You can do it at a lower level, but you shouldn't. And you should, basically, I'm creating a little file here called, so just an example Python module now, not connected to the maze example, called greeter.py, just to show how argparse works. And how argparse works is you create a parser, and then you add each argument to it. And it follows the standard for how switches at the command line should work. So if people don't know how switches at the command line is supposed to work, each option should have both a single letter label introduced with a dash, or a double letter label, or sorry, a long label, a word long label introduced with a double dash. So here I can say greet minus T doctor, or I can say greet minus minus title professor, and they do the same thing. argparse knows about that stuff. How can I stop Slack sending me notifications while I'm teaching and it's being broadcast to the internet? There we are. So the next thing to do is you call this parseargs, and that pulls anything in from the command line and renders an object, which you then address with the arguments object dot, and it gives you the value of each parameter. Okay, this is fairly obvious once you see the dot cry, but it's important to know that it exists. So this is a part of what you should do with your when you're doing packaging, and it automatically makes quite nice help for you. Okay, so that's something you should do. So I better switch to this version. Yeah, good. OK, so back to this question of laying out a project. So here we're doing the greetings example. So we said we need to create a folder with the name that we want the package to have, and that's one level down from the top of the GitHub repo. So there's a bunch of stuff in the top level of the GitHub repo, which is not the Python package itself, which we'll go through in a minute. The individual bits of code that we say, so all the maze example, go inside some package name there. This is always an all lowercase word for the package name in Python like that. So we make our directory structure, and then we need to make a setup.py file. And a setup.py file is the thing that you use to install it. So when you will have installed other people's code, and you might have done python setup.py install or pip install foo, that's getting the metadata to do that from here. And basically, it contains some metadata and a variable, which is the list of files to include in the installation. Right? You can make this list manually, but if you do find packages, it will package up the bits that it will package up all the Python files below that, below a certain point in the file structure. Normally, you exclude the test files when you ship. So when we look at testing, we'll make a bunch of files that did testing. We don't enclose those in the ship package, because you might have dependencies that you need for testing, but not in actual for the use in the running code, and you don't want to get those mixed up. So the point is, having run that setup.py file, I was able to do Python setup.py install, and then it's available as a module, but also it's available in the shell to run as a command installed throughout the system, so I can open a new. So it's just the same as if it was a command that was installed from elsewhere. And now, another really important point is, at this point, you might be thinking you want to submit this code to PyPy, right, the Python package index, and make it installable, but you don't have to, because pip, the Python installer, can take a GitHub URL. So long as your code is pushed to GitHub and has got a setup.py file in the root level of that GitHub repo, you can pip install directly from GitHub while you're practicing before you actually publish it to PyPy. So that's a nice way of, if you need useful within a project. So we've taken our code out and put it in a module. We write an executable command line script. And now we need to do a few more things in our setup.py file. So we need to add install requires and then the list of names of libraries that the thing depends on. Okay? So this is how, when you do pip install on other people's libraries and it goes chug, 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 and installs any dependencies automatically, right? So you don't have to manually work out which things I also need and go and install them first. The way you specify that is in this list here, okay, in your setup.py file. We added a command line entry point, so we need to specify the package and the package name, the module name, and the function name that is going to represent that command line entry point. So this is the greet command that I put on the text file on entry. How did it know that that particular Python file was the one that command should be when I did the install? That comes through this. Okay, so that's what this is here. So this is a string which says the name that the command should have in the shell is equal to, and then the path within the Python module. Okay, so that's kind of the actual Python-y bit, and then there's some best practices that we should follow as well. So always have a README file, right? It's kind of obvious. In your README file, you should usually explain the basics of the usage of the package. So that's where you would document how you use it. And we'll go on to talk about documentation in more detail in a moment. You must include a license file. And we'll talk in more detail about some of my opinions about software licensing. Now, I'm not a lawyer, but I have some opinions about software licensing, which we'll talk about in a minute. But you must include one. It is extremely frustrating to go on the internet, search for somebody else's implementation of an awesome algorithm, find the code, right, in GitHub or Bitbucket or wherever, and it not have a license file, and you have no idea whether or not you are allowed to use it, right? It's nearly useless. So at least include some license. We'll talk more about how to choose which one in a while. And this is something in particular for research. And this is something people in the wider software community wouldn't think of. There's a format we're trying to introduce in research software. A colleague in Southampton first proposed it, called a citation file, which is how to cite your code in papers that use it. Right? Now, software citation is an extremely rich and deep subject. There are ways to generate. So, do you cite the software directly? How do you get a DOI created for some software? Do you publish this? Do you cite the journal article that describes the software? Right. So there are journals like Journal of Open Source Software, Journal of Open Research Software that exist purely to create something that looks like a volume and an issue and a page number for the purposes of citing software. But there are now new proposals so look at this. If you look at this code meta.json, this is a standard for actually allowing software itself to be a proper academic citable object with a DOI for the GitHub repo. And there's a collaboration between Figshare and GitHub to allow you to automatically create DOIs for GitHub repositories to make them into citable entities. Okay, cool. So software citation. Yes, so it's a very interesting topic on what the best way to cite software is, whether it's to write a paper around it and then cite the paper or to cite the software itself, and how to do that. Whichever you decide, it's important to tell people, right? And there's and the citation.md file is the standard that's been recommended for the human-readable side of that. Code meta.json is an attempt to make a machine-readable JSON file that you put into the top level of the repo in order to provide citation metadata for software. We'll talk about testing later, but writing unit tests should be part of when you do your package. Let's not talk about distributing compiled code now. Let's instead talk about documentation. Right, so documentation. So a very common thought is, oh, I don't really want to release this code because I then have to write proper comprehensive documentation, right? And that's a massive burden and pain and really difficult and slow and time-consuming. Do not worry about that, right? There are two important bits of documentation to write, and if you get those right, most of the work is done, okay? People who make really good documentation. I used to work for the MathWorks. Some of MATLAB is my fault, sorry. And we had one doc writer for every coder, right? That's what it takes to pay for good software documentation. In academia, we can't afford that, right? So therefore, we need to find a way of achieving decent documentation in a manageable way for our software. And there are so in my opinion, bad documentation done on the cheap, can often be detrimental, and here's why. It rots really fast. It goes out of sync with the code, because we update the code and we don't update the documentation. And then I go along and I read the documentation and I'm thinking, well, I know how to do this because I can read the documentation, and you go and try and do it and it doesn't work. That's annoying, right? So what kind of documentation can we write that stays up to date with the code, okay? One of them is unit tests, and when we come to unit tests, we'll look at how testing is a form of documentation. But another is a simple, what they call a vignette, a simple example analysis done in the README file of how to use this library to do something. Just do one of those, right? And you can make that executable, right? Because you can set that up so that if you the code that forms that is run using for example, using you can do it in a notebook and then have your makefile scripts turn the notebook into the README, so dumping that text out. And then you know it's reliable. You know the code will actually, you know, there is a connection between those two. So that's a really valuable thing to do. The other thing to do is to use comment-based documentation tools. So this is tools where at the beginning of every function or class in your code base, you write a little bit of text that describes how that function is, and it generates a website from that. It generates HTML content from that documents each of the functions and classes in your code base. Okay, Doxygen is a popular one for some languages. Let's just look at a package. So it generates stuff like this. So for each of the different functions in the code base, you get a little description showing all the different inputs and any text you decide to add. The common Python one is Sphinx. What happens is at the beginning of a function, you stick a doc string. So a doc string in Python is the stuff that comes up when in notebook or in the shell you type help name a function. If the first line of a function definition is a string, multi-line string with 3 quotes or single-line string with 1 quote, that's the text that comes up when you type help so-and-so in the notebook. With Sphinx, you can design, it takes a special format for those such that it goes parameter name, parameter type, and then a description of what the parameter name is and what kind of thing the thing returns. If you write this for each of your functions and then use Sphinx to automatically generate that documentation, I'm having to go fast because of the content we want to get in. So it uses a certain Wikitext format called restructured text. It generates the documentation, and you get output like that, and then you can style it, right? This hasn't got any CSS on it, so it's not looking very pretty, but then you can style it. And that is that's the best way to get documentation, and it stays close to the code, right? Because the place where you're writing that documentation is in the code base inside the function, it's less likely to rot, right? You're less likely to add a new parameter to the function and forget to put it in the documentation, okay, rather than writing documentation outside. So these three things are my recommended approach to affordable documentation for research: comment-based documentation, a vignette README made executable if you can, and writing unit tests, which will see another form of executable documentation. All right, now I wanted to. What time is it? 10:44. Let's do that later. Let's do licensing. So I mentioned that you need to put a license in your code base. So I am not here to give the official software licensing policy for your institution to know, who, for example, in your institution, who is allowed to publish software and put a license on it. Most universities, officially, only very few people are formally allowed to sign contracts on behalf of the research institution. And when you stick a code on the internet and put a license file on it, you're formally doing that. In practice, everyone just assumes PIs are allowed to do that, right? So your PI says it's OK to stick a license on your code and stick it on the internet. You'll get away with it. But it's a dodgy gray area. That's what, in practice, I would do. If you're a postdoc or a PhD student, get your supervisor to say so. Because to prove that I follow my own opinions, as I say, everything in my lecture notes is published under the Creative Commons by license. So you can use it. Right. The most important thing about licenses is to choose one. It doesn't really matter what. Some objections people will give you to sticking your code on the internet include the fact that, but we want to make money from this code, right? That is not a blocker to publishing your research code. In my opinion, this is just a personal opinion, research code should be published because research is, the government's paid us to do this. But more importantly than that argument, I cannot tell if your research is rubbish if I can't read the code, right? Because I reject, when I referee papers, I reject them if I can't see the source code, right? And I recommend that to everyone. At the very least, the referees of papers should be able to see the source code. Okay, that's still largely not, often not the case. So in my opinion, for the reproducibility argument, the fact that science needs to be trustworthy, that's why research code should be published. But it doesn't stop you making money. There are lots and lots and lots of awesome ways to get your nice money that you deserve for your awesome work and still open source the software and thereby not betray scientific reproducibility. You can publish it under a nasty license and then offer it under a more gentle license for money. You can publish the code for free and then use that to generate yourself a nice consulting business. You can do what VTK do and sell the manuals at very high price and not have good documentation on the internet. I don't recommend that one, but it is a working business model for some companies. You can sell the basic version, you can publish the basic version and then sell add-ons. There's lots of different things you can do. Next argument against publishing your code, people will say, is worried about people stealing your work, okay? That's not your problem, right? Your problem is not that someone's going to steal your awesome work. If you look at the probabilities of that happening, it's much less likely to happen than nobody on the planet ever having heard of you, right? That's your problem, okay? And the best way to make it more likely that someone will cite your work, and if you're a researcher, I'm assuming everyone here is in research in some kind of space, that may be incorrect. If you're a researcher, then getting citations is the thing that you want, right? And you are much more likely to get citations if the stuff is out there and citable. So are you more worried about anonymity or theft? I am far more worried about anonymity than I am about theft. The other thing that's important is people often say, oh, well, my code's not good enough to share, right? We all write shoddy code that's full of bugs, okay? My old supervisor at the MathWorks used to say to me, if you ever come across a developer who says they write bug-free code, run screaming, right? because they will not be doing the... Software engineering is about the practices we do to work around our own incompetence. Right? That's basically what it's about. Right? If we recognize that we write shoddy code that's full of bugs and then come up with ways of working to work around that, right? That's what we do. And the main thing that will make your code better is other people reading it. Right? So it's really, really important to get over that kind of your code is rubbish. I mean, I'm supposed to be a professional scientific programmer. Largely, I'm a manager now, so I don't write code very much. But when I do, it's definitely full of bugs. So everyone else should feel comfortable. Here's what you should worry about. You should worry about license proliferation. One of the things that's annoying in scientific software is Professor so-and-so decides to write Professor so-and-so's software license. And it's different from all the other software licenses in the world because Professor so-and-so has decided that he wants the terms of use for his thing to say that it can be used by grad students on Wednesdays and Thursdays, and it can only be used by commercial entities if they write him a love letter on pink notepaper, and this kind of thing, right? And not really, right? But there are projects that do that kind of thing. Don't, because there's a problem called license proliferation. And what that means is that if I want to use this library that does this awesome algorithm and this library that does this awesome algorithm and combine them together to make a super analysis that's dead clever, and the licenses are such that I am not legally allowed to use the two together, which happens, right? Then that multi-mixedness of licenses has stopped me from doing awesome stuff, right? So when you choose your license for your publishing your software, pick from a short list. GitHub has a tool to automate. As soon as you create a license.md or license.txt file in GitHub, it pops up a window saying, would you like to choose BSD or GPL or one of a bunch of other ones? Pick from that list, right? Then at least you're not proliferating licenses willy-nilly. Please don't make up your own. Unless you are a lawyer, you cannot safely write your own software licenses. One thing to think about in the context of software licensing is, do you want to require everybody else to use the same license as you, who builds on and modifies your software? That's what we call virality, right? Does the software, is it infectious, okay? Licenses in that category include the GPL. Licenses that don't do that are things like Apache and BSD. It's up to you which one you want to use. Basically, if you want to be commercialization friendly, you want to use a permissive license. If you want to be more committed to making everybody else work in the open, you want to use one of these copyleft licenses. My recommendation is to use BSD for everything, or similar, use a permissive license. That's my preference. But I don't want to interfere with you choosing your politics on this, right? But pick from that short list. That's what I'm trying to say. There is no license out there which is a standard license that's well used that stipulates for academic use only. There isn't a way to do that well in law. Copyleft licenses are usually, if you want to do something similar to academic use only, that's usually your best bet. I'm not going to talk about patents. I'm really not a lawyer. It's a scary topic. Talk to your lawyer. So I talked about citation files. Oh yeah, one other thing to think about when you're thinking about your research project is people often think, right, I've done this awesome project and I need to make sure it gets maintained. I'll throw it at the internet and hundreds of people are bound to come and help maintain my code. This doesn't happen. If you want to make a sustainable software project, we can talk more about that. There are good techniques about how to build a community around your software. The best thing is to go onto the online lecture notes and look at this link from the Software Sustainability Institute, which has a long discussion about how to build community around software. 10:52. I will talk about issue tracking as another important part of this sort of topic of making your code from being something that just you were using in a notebook into a published piece of code. If you're working with other people, it's important to be able to have a place where you can keep that list of bugs and manage that list of bugs down, okay? You want to use a proper issue tracker in GitHub or whatever tool. I just recommend using the GitHub one. So you will want, for each bug that you find or task that you want to do, to find some tool which allows you to list who it's currently assigned to and who reported it. The most important thing about using an issue tracker is nobody does any work on anything unless there's a ticket assigned to them with their name on it. Right? Let's look at the Jupyter projects issue tracker as an example. So I just picked a random issue. So somebody from the internet said something had gone wrong with the thing. It's not assigned to anyone here, so that's not going to. They said, let's find one that's assigned to someone. Assignee. Let's see what Fernando's got at the moment. Nothing. Thomas, let's see what Thomas has got. 5 closed issues. There we go. So I'm just randomly exploring somebody else's code base's issues now to see an example of a good example. So somebody's reported something, it got an assignee, they worked through it, and in the end it was closed, right? And the solution was merged in. So we'll talk about GitHub Flow in a minute. But this is what you should be doing, right? You should be using an issue tracker like this if you've not seen them to manage the different issues in your project, the different bugs, the different tasks you have. You can label up. I'm not a contributor to that repo, so I don't have the right to assign a label. But you can label up different tags on things. So here, this one has been tagged in status needs review, right? So it said somebody's done the coding and somebody else now needs to review it. Somebody else needs to look at the code before it's allowed to come back into it. That's another good practice. And you can use these tags to label up the different issues in the different categories. Okay, this is a bit best practice you should be trying to do for basically for any project that's got more than one person working on it. You should be trying to use something like that. All right, so that's going to be my talk on taking code from a notebook that you've made yourself and trying to turn it into a downloadable package that other people can get. Let's do questions on that and then take, are we doing 10-minute breaks or 10-minute breaks? Okay, so let's do questions on that first topic and then do 10-minute breaks. So questions. Yep.
When you're working your notebook, kind of writing all this code without worrying about the packaging stuff,
yeah.
At what stage do you think, right, this is, because obviously there's still work to be done in the package.
Yeah.
So it's not like a finished product.
Yeah, no, exactly.
Where do you draw the line?
So for me, whenever I am about to go into open another notebook and thinking that it's a good idea to copy paste some code from one notebook to another, that's the moment when I'll take the code from the first notebook and turn it into a package. Yeah. Yeah. Although he's now thinking about several times recently when he hasn't done that. So. But yes, that's the rule of thumb. Anything else? Yes.
You briefly mentioned if it doesn't have a license file, then you don't know what to do.
Mm-hmm.
I would have thought if it doesn't have a license file, I can do whatever I want with it.
No, that's not correct. The default is copyright, all rights reserved. I do know enough law to know that. Again, I'm not a lawyer, and if anybody watching on the internet wants to say that anything I've said about the law stuff is wrong, please comment in the comments below, I'm guessing. But yes, yeah. Yeah.
If you have a new algorithm that you want to integrate with existing library, then how do you cite the new algorithm? Do you cite the original library or the commit or something?
So the question is there's a library with multiple contributors, is that right?
You know, for example, there's a library that does something,
Mm-hmm.
and you have a new algorithm to do that something. So you write a code for the new algorithm and push it to the existing library.
Uh-huh.
So when someone will cite your algorithm or your implementation algorithm, does the person cite the library or you commit to that library?
So there is a long discussion of this in the software citation community about because software is a flow, right? And our model for academic publication individual static snapshots, right? And so that's one of the places where so does a software citation cite this software project as a project or a particular release? The GitHub commit hash, is that the citable entity? Yeah. So that's one of the questions that Dan Katz and colleagues on the software citation project have got some thoughts on. I'm glad you imagine the scenario was that your modification you pushed to the existing project. That's at least better than what most people are doing, which is writing a completely new independent project and forking it. So well done for thinking that you're going to commit your code in as a new option or some new parameters into the existing code base. I can't remember what the software citation project said is whether it's recommended to, no, I remember what Dan said now. So they would like to establish citation chains. So rather than, if I use A, which uses B, do I have to cite both A and B? Or do I cite A, and then A will cite B? And they said that the second solution is the better one. So citation chains. But yeah. Sorry, that wasn't a clear answer, but that's the best we've got at the moment. Yeah. Yeah. So I rubbed the URL off the whiteboard, didn't I, when I was talking? The URL is right. I can't increase the font size in the browser's address bar, but it's github-pages.ucl.ac.uk/rsd-engineering course, where minus is the minus sign dash, right? So github-pages.ucl.ac.uk/rsd-engineering course. Yeah.
So there's kind of a lazy medium which I've used a lot of times, which is where you dump all the functions you're going to use often into a .py file and then import that, but you don't go through with all the setup tools and all that. Which cases would you recommend that for? When do you recommend actually doing all the packaging, or always?
So honestly, I wouldn't recommend doing what you've just said. Because I'm obsessed with readability of code, right? And I think as soon as you're starting to make code that you're going to reuse, you in the future counts as another human being than you, right? In those circumstances, finding where the code is becomes an extremely important thing to do. And by breaking it up into files, you're saving yourself that future day, several future minutes, which integrated over old time will probably be quite a long time, of scrolling up and down through the file to find where the bit that you want to change is, right? And anything which has helped us get away from the entire code base in one source code file thing is better. So honestly, please don't. All right, I'm going to take a pause there. Any comments on the sort of format of the class that will help me do a better job of the second part in terms of pace or anything like that? People feeling it's basically useful or quite dull? Feedback's good. OK, cool. So.
If you want some feedback, I mean, I'm close to the end of my PhD, and I really wish I would have had that like 2 years ago. So.
Awesome. That's what we like to hear. Thank you. OK, 10-minute break, everyone. I'm first in the queue for the coffee machine. Lecturer's privilege. If your Git ever goes wrong, you've made a mistake, and you want to ungitify a particular folder, just rm-rf.git, and the project will not be a Git repository anymore. So I'm going to make a little file called mountains.txt, and I'm going to put in it some information about mountains. Git add mountains.txt. No. There we are. So I've done git add mountains.txt. What did I just do, right? People sometimes miss out on the theory of how Git's working a bit. So by adding a file, what I've done is I've said, include that file in the next commit, right? And I've moved that information into a place called the staging area or index, which is the place where the changes that I've made that I want to include in the next commit will sit. Well, why might that be useful? We'll see. I'll set up an example in a moment of why that's important. Then I do git commit -m initial commit of mountains. And that's moved the information from the staging area, whatever information was in the staging area, into the commit, into my local repository. So that information is now sitting as a commit in my local repository. It's not gone to the internet yet. I'm now going to, on github.com, two-factor authentication, very important. I'm now going to create a new repository on GitHub, teaching Turing inst nov17. And I'm creating a repository and I've pushed my code up so that the content that I wrote on my laptop is now up on the internet. Okay, so that's the basics of starting my version control up. I'm now going to make a series of a few commits just to build up some content in this repository and talk about a few Git issues that people might have missed. So So I've now got some changes in mountains.txt and a new file, lakes.md. And I've got both of those changes in my repository. And there's two separate tasks. If I commit everything now, I've got two relatively separate pieces of work that don't interfere with each other in one commit message. Okay, that's bad, right? That's why Git leaves you the option of deciding individually which files to include in the staging area, so that if you accidentally, in your own head, do work in a slightly scatty way, you can backhack things in the commit history so that it looks like you were working in a much cleaner and nicer fashion. So if I now do git add lakes.md, and if you come from Subversion and that kind of thing, which didn't allow this stuff, then you might be confused. You might be confused as why is Git making me do all these extra stages? It's this flexibility. So I've now got to a status where only the mountains.txt file, out of files that have ever been mentioned as interesting to Git before, has new content, right? And that's when I can do git commit -am add first mountain, and git commit with a -a switch is include automatically in the staging area as part of the commit. So fold my git add step and my git commit step into one, including in the git add step any files that had ever had any changes in it mentioned to Git before. Okay, and that's how it decides. Does that make right? So most of the time, if you just want to do, just include everything, you just do this all the time: git commit -am and then your thing. But people don't realize the importance of the staging area and the reason why you have this working directory, staging area, local repository separate with your add and your commit stages separately is so you can do that restructuring of the of which, specifically decide which individual changes to include in the thing. And in fact, there are, I won't show them now, ways to include individual changes to a particular file. So if you in a long file, you've got a multiple change on between lines 5 and 10 and changes between line 25 and 50, you can include one of those changes in the staging area and not the other. It's not just on a file by file basis. So there are switches that allow you to do that. Anyway, I'm now going to push. Okay, so I'm not doing Git from scratch properly, right? Because almost everyone put their hand up and said they were using Git at all. I'm just showing you a few extra things that people may have missed in Git. The next thing I want to show is how to undo mistakes. So I'm going to open my mountains file, and I'm going to add a lie about a mountain. Right? So this is simulating if it was a coding exercise that I've actually made a mistake. And that's pushed. So there's nothing I can do about that now. I can't rewrite history. I can't get away from the fact that that's a published mistake. I'm going to carry on doing some work. I'll come to that in a second. Let me just build this example up. So add another mountain. OK, so I've now done some work after my mistake, and I haven't noticed my mistake. Right? Now what do I do? So to answer your question, push takes the information from the local repository, which is the archive of commits sitting on my laptop, and transfers that information to the remote archive sitting on GitHub in the internet. So Git is what's called a distributed version control system, which means the full history is kept on every copy. So my laptop has the full repository with all of the story in it, right? It's not the case that it only has the current snapshot on my laptop. So until I push, if my laptop were run over by a truck, the data would be lost. Okay? It's the act of pushing that synchronizes my database of Git commits on my laptop with the one on github.com. So git add takes changes and blesses them and says the next time you do a commit, include this change in the commit. So not all the changes that I have made will go into the commit. Only the ones I've added will. So there are three. This is the thing that people often don't get in Git when they get started, right? There are four different places actually that information sits. There are 5 things you should know about the right. There are the local working directory, the actual content of the files when you edit them. That's the first place. The staging area, which contains those sets of changes which you have used add to say will go into the next commit. The local repository, which contains the series of commits you have made and sits in the .git folder as secret metadata on your computer. And finally, your remote repository, which is the one on GitHub. To go from working directory to staging area, you use git add. To go from staging area to local repository, you use git commit. And to go from local repository to remote repository, you use git push. Right, so I've now got this mistake. What do I want to do about my mistake? I would like to include a commit which fixes my mistake, right? And I do not want to scrub the fact that the mistake existed, because this gives me a record of for what versions of the code did that bug exist. And if I want to make my research auditable, I need to know which of the papers that I published between 11:25 this morning and 11:30 do I need to retract now, right? And this gives you that that record. So let me show you what I'm going to do. in my Git log, I can see all the commits that I've made. Each commit has a unique code, which is a hexadecimal string. I need to specify the hexadecimal string of the commit that I want to revert, which in this case is the add a lie about a mountain commit. That has the hash code 4A7, F0, E9, E5, etc. I only need enough characters to uniquely specify it. Git revert 4A7, F0. So that's attempted to do an automatic revert, and it's not managed to do so. And I now need to do the usual thing of fixing up a conflict in my file. And as always, it's marked the area around where the problem is with this less than, equals, greater than. And this is the same thing you get when you merge, when two people work on the same file and you need to resolve those conflicts. So sometimes it will do it automatically, and the algorithm won't need help. When it does help, it narrows down the part of the file it needs help on with this less than, equals, greater than. As the person fixing up the problem, it's my duty to edit that file, remove the less than, equals, greater than cruft that Git has added, fix the code to be correct, and then git add the file to indicate that I've completed my conflict resolution process. If I then do git commit, it will automatically, this screen's become a bit dirty, but it will automatically add a commit message for me, which has got the right text on, which here says add a lie about a mountain is being reverted. So now in my git log, let's just push all of this to the internet. So now in my log, I can see the revert commit and the original mistake commit are part of my commit series. Yeah.
So when you run the commit after you've run a revert that doesn't automatically revert, the commit is including that revert statement in it.
So in this case, it wasn't completely automatic. I had to do the manual fix up. The add indicated that to the system, it was reusing the word add, confusingly, to mean kind of declare that I've done the fix up that I need to do, right? So that said that told it that the fix up was done, but I still need to commit that change to the local repository and then push it. Normally I would do git commit with a message, git commit -m the commit message. Because I knew I was doing a revert commit, I knew that it would have an automatic message ready for me, which would always be the default is revert, open quote, and then whatever the commit message was on the one that it's fixing. Is that? Yeah. Yeah. So that's git revert, which is a fair number of people don't know about. It's quite, I think, quite useful. Let's try our GitHub Flow pull request example now. Okay, so what we're going to do is my collaborator, who is called Pardon me? Kenan is going to clone my repository. So you'll need the URL. The URL for the repository is github.com/jamespjh/teaching-turinginst-nov17. If you can clone that onto your computer, okay, so if you now make a change to the code and try and push it, it won't work because I haven't given you write permissions. Right? So you'll get an error message saying you're not allowed to make this change. Right? I could give you those permissions, okay, but I don't want to do that. Right? Instead, what we're going to do is you're going to make your own copy of the change, push your changes to that, and then I'm going to review and accept them. So it's a different collaboration model than the one where I make you a blessed contributor. So to do that, the way you do that is you hit this button here on the top of the screen that says fork. So you go to My Repository, and you go up here and you go fork. Hit that fork, clone the fork onto your computer, and so if you fork, what you'll get is, now let me see if I can demonstrate this by forking this version on me into somewhere else. Nah, it's going to be too slow. All right, well, Kenan's going to fork it. So Kenan is now hit the fork button, and that's what that's done is, Kenan, if you can tell me your GitHub user ID once you've forked it. And
So KDIREK.
KDIREK. So here you see, I'm now on Kenan's account on GitHub, not mine, and he's got a copy of the repository on his account, right, by pressing the fork button.
Sorry, I have two copies. So when you were doing this before, I forked the repository prior. So
Okay, fine. So whichever one of those you want to use, it doesn't matter for this example. But what I want you to do now is make a commit of your own in theme, so add a mountain or a lake to one of the files, and commit and push that to the clone on your computer of your fork.
Yeah.
Kenan's fork is Kenan's change, right? He doesn't have permission. Am I on again with sound? Yeah. He doesn't have permission to make changes directly to my repo, right? But he can push onto his fork. Yeah. And now what you need to do is open the pull request window on your fork. I won't have the. Do I have the power to do it? Yeah. So Kenan would now do this, but I'm going to do it. I'm just going to use the interface to do it so everyone can see. I've opened a pull request to merge into my fork from Kenan's fork. Yeah? So Kenan would do this, and this requests that his change be considered by me worthy of incorporation into my project. And we can now have a conversation through this thread, right? So imagine I were now commenting. I could say, some comments on that, and then hit this button, and that merges his work into my copy, right? And that, if we now go back to my copy, it now has Kenan's change in my copy, okay? And that is how we collaborate on GitHub with projects that have got many tens, hundreds of contributors in. Right? The other model you may be used to where you add certain individual people as contributors and then they can all commit is much weaker than this from the point of view of anyone can propose a change and then the owner of the project reviews those changes, can discuss through this interface, comment on individual lines of code. Did you see how I clicked on the plus in the commit? And I can comment on a line-by-line basis to discuss the changes and then accept them or reject them and go back and forth, commit addition, and Kenan can commit changes to his change, right? And they will be included in, until I'm happy with it. Do you see? So that's how we do this GitHub Flow collaboration, and it's, I think, transformative to the ability of human beings to collaborate on code projects, is this particular form of collaboration that's done through GitHub Flow. So everyone should be able to, now, if you notice any typos or spelling mistakes in my lecture notes, go to the GitHub URL for my lecture notes, which is, hello internet, github.com/UCL/RSD engineering course. Which is not the web page where you go to see the lecture notes. It's where the Jupyter notebooks are that I use to generate the lecture notes from. You can make changes to those by forking my lecture course, making your changes and sending me a pull request. So if anyone sees any material today that they thought was wrong, please send me a pull request. This is how we work. Okay, so that was what I wanted to talk about Git and version control. There is one other thing which I won't have time to do today that I like to mention to people, which is something called Git bisect, which is a way to tell Git to automatically find which of the several hundred commits I made between January and June this year was the one that introduced the bug by automatically running a test and doing a bisection algorithm to find out which one of the commits introduced the bug. So that's in the lecture notes as well, worth looking at. Questions on Git before I move on to testing?
What if two people forked the same copy that you have, but they propose conflicting changes?
Yeah.
Or you commit the changes. How would the second one? It might not be conflicting, but how would the second?
So we can practice. We could practice that now if we wanted and do another example, but I think we won't have time. But when I do this in the full 3-hour class, then we exactly engineer that situation so everyone. If two people are making conflicting changes, whoever pushes first gets in. Whoever pushes second gets a message coming back when they try to git push. At the moment when you try to get push that says rejected, ! You push second. Life sucks. You then do git pull, right? And you get the other person's changes, and it sets your repository up with that less than, equals, greater than stuff around where the conflict is. You resolve the conflict, git add to indicate you resolve the conflict, git commit into your local repository with your fixed changes, and then git push again. If you're lucky enough, nobody else has pushed even more conflicting changes in that interim, and your change gets in.
Can you sometimes get deadlock where lots of people are?
You can't get a deadlock. You can get a situation where it's quite hard to get your changes in. Under those circumstances, what you then need to do is use a branching strategy. So we didn't look at branching, but we can do git branch and pull off a branch, right? And then I can have one sub-project be working on a particular branch and then integrate those branches later. Yeah, so instead of having just one main line and everyone merging into that, they're merging into their branches and then kind of pushing up the pyramid. But that will only happen when you are hundreds of people project, right? Yes?
So when you publish something, you can revert the changes you made. Is there any way of completely wiping it from the history?
Yes, don't. Okay. So there are commands which will allow you to rewrite history, right? The only circumstance I ever think that is acceptable to use it is on the rare occasion when I committed my password accidentally to the Git repo. And then if I just commit another commit now, which removes my password, that won't help because the password will be all in the history. If you look in the lecture notes, it talks about something you can do called an interactive rebase, where you can expunge a commit completely from the history, but then you need to force push it. And the problem is if anybody else has cloned from your repo in the interim, their version will still have the bad data, and they will have an inconsistent history with yours, and they will either need to destroy their work or re-overpush with a force push back, reinserting the bad information again. So the right thing to do is to let there be an audit trail about the mistake, right? Possibly, if you've written a very rude commit message about your PhD supervisor or something like that, then it's useful to use the interactive rebase technique. But for the most of the time, you should be letting the audit trail exist. Yeah.
Do you have any thoughts about the use of Git for versioning of data, specifically text data?
Right. So that's a really, really deep question. So version control of data is not yet a solved problem, in my opinion, at all. Right. So Git has Git large file system and Git annex, which are potential solutions to allow you to include to work with high volume data. Git only gives meaningful changes on line-oriented data. So human-readable, non-binary data sets where the changes are where the changes are on lines, where it makes sense to look at the differences at the level of lines. And it only really works where GitHub's limit, I think, is 100 mega file, I think. So if your data falls into that class, which for some kind of corpus-oriented data, XML data, that kind of thing, it does, then I think Git works very well as a tool for that. Otherwise, it doesn't. And I am not there yet with a solution I'm happy to recommend for version controlling large data sets. I just don't, there's nothing that, I certainly think it's something we need to do. And the kind of methods we're using so far, I don't think are scalable. But if you're within that sweet spot, line-oriented, human reasonable text data in a reasonable character set with files that are small enough to fit in the sort of 100 meg kind of level, then Git's a good solution. Tell you where Git is a good solution outside code. It's an excellent solution for co-authoring papers. So if you're working in LaTeX or Markdown or some other textual format, I strongly recommend the Git approach to co-authoring text versus, say, track changes in Word, which I think is pretty awful. Anything else on version control? Yeah.
So let's say we have access to repository, and so like for collaborating with others, is it still the right way to use fork, or like is it also better to use opening a new branch and developing there and then?
So I don't mind between the branching versus forking too much. I do think it's important to use pull requests, right? So I don't see myself a reason to carry on using the thing of, in Git you can just add somebody else as a committer, so they can just commit directly to your repository without needing to make pull requests at all. But that doesn't create any kind of opportunity for code review. And we've seen that the interface there with that message thread was a very nice interface for code review, right? Almost all code we ever write, somebody else should read, right? It's just a really good idea. It's a learning experience for both parties. It's best done with somebody, with a peer, right? And so I would recommend against just directly committing without going through some kind of code review pull request process. Whether you do that through forking or a feature branch, so you git checkout -b name of my new branch, and then you commit to that branch, and then you do the pull request from the branch into the thing rather than through a fork. That was a very fast compressed sentence. Sorry, that probably didn't make sense to anyone. But there's another way of doing it that doesn't involve forking. I don't mind too much between those. The fork button's nice on GitHub, but it requires you to be using GitHub or GitLab or one of these tools that supports that kind of thing.
Is there a way for versioning log files?
Versioning?
Log files. Logs generated from a program. For example, if I want to know how my changes affected the running of a particular program.
Oh, I see. Interesting. I haven't done that, and my knee-jerk response was going to be, I never version control commit generated files. I only ever version control commit the things that I'm writing, and then the stuff that computers generate I don't commit. But what you're looking for is looking at the differences. So of course you can use diff at the text prompt anyway to get those differences. But yeah, I can see circumstances where committing, perhaps as part of a build process, or if you're using we'll talk about continuous integration in a minute, where you automatically teach the computer to do various processes repetitively, it could be very interesting to commit those kind of log files. I haven't done that.
If you have a compile program and you want to generate the compile warnings and the errors over different...
Yeah, so actually I think I know what the answer is. No, you shouldn't version control commit them, but you should have them be build artifacts in your continuous integration service. So tell Jenkins or Travis that those things are build artifacts, and then that will be able to show you the differences between the different builds of those build artifacts. But let's come back to this when we talk about continuous integration, when we talk about testing, because most people in the room will be able to appreciate this conversation more in half an hour when we've shown some Travis examples.
Another comment to what you said about interactive regex.
Mm-hmm.
Some repositories ask us to reverse all our commits in a single commit before.
Yeah, so again, in the lecture notes, there's details on how to use interactive rebase to squash commits. But I did. You know.
You're planning to make a lot of changes to something. Is there a way of telling everyone don't do anything with this file at the moment?
So that's where you should use branches, right? If you're going to be doing a kind of long-running big chunk of work, open a new branch, do the work in that branch, and then when you get to your integration step, you're then merging the branch into master. Normally what you do is merge from master into the branch and then merge back, so that you're less interfering with the kind of main flow. Sort of the kind of lock handling approach, where you say, hey everyone, this is mine now, don't touch it, is there's no need to do that where you can create branches, right? And Git is much, so the big difference between Subversion and Git is very, very comfortable with many tens of branches. Branches are a very light and easy thing to do, and because merges are so effective, the automatic merge engine is very powerful. You shouldn't worry about branching. Branching, normally my workflow is if I'm working on pretty much anything, I'll open a branch for that task, and then I'll merge that branch back in when I'm happy with it. So let me just show how to branch. So here I am on my thing, and I'm going to git checkout -b a new branch. I better give it a text name. New branch. There we go. Git checkout -b new branch. I'm now committing on new branch. So if I edit my mountains file and add add another mountain and and I've committed that onto my branch. So if I now switch back to my master branch, it's not there. It's only on the other branch. Yeah? I can now push that branch up to the server. So this is the switches to push that branch up to the GitHub server. And I can now file a pull request, not from somebody else's fork, but from my work on that branch. And it won't let me automatically merge here. Can anyone understand why? So the version on the server on the master contains Kennan's work. But I never pulled Kennan's work down onto my laptop. So when I took my branch off from the point before Kennan's work was included. So now, if I'm trying to merge my branch into master, I can't do that because I've got the master's got Kennan's work in. So there might be a conflict there. So in order to resolve that, I need to, on my branch, do, first of all, git checkout master, git pull to pull Kennan's work down onto my local master branch, then go to my new branch, then do git merge master, which is going to pull Kennan's work onto the copy on my laptop of the new branch, which created a conflict, which I'll fix. So there's my Mont Blanc work, and there's Kennan's work. We want both of those. Git add, git commit. Accept the automatic commit message as being the default merge commit message. And now I'm pushing that merge work up onto my branch. And now the branch contains all work that was in master and some more work of its own, and therefore it will be valid to merge it. So that was a nice little example of the way those different routines work. And you can draw out the graph, right? Git commits form a graph. So here I was working on master. Kenan forked it. Meanwhile, I made my new branch. Kenan did some work. I did some work. I merged Kenan's work onto master. This wasn't allowed because this contained some work that wasn't here. So therefore, I pull again from master onto my branch and then merge that back. OK, let's do testing. Yeah, good. OK, so let's get started on testing. All right, so the purpose of testing is to find any mistakes, is to engineer around mistakes, is to find ways of automatically discovering when I've screwed up. It is not about proving code correct, right? There's a whole other field of awesome computer scientists who I really like who are interested in proving code correct. That is not what we are trying to do. What we are trying to do is prove code wrong most of the time when it is wrong. And this is, extremely powerful in terms of increasing the likelihood that our code will be right. People will say, I don't want to bother writing tests because it takes me time to write the tests, and I don't have the time. Testing saves time. And moreover, the kind of time you get is happier time, because one day you will discover a bug. And if you haven't got any tests, you will have no idea where in your enormous code base that bug is. And you will have one of those days, we've all had them, where you discover something is wrong with your code. And so what you do is, you know it's somewhere in this code, my code is wrong, and I have no idea where. So I will sprinkle a very large number of print statements through my code and gradually narrow down on the bit of the code that's wrong and eventually fix it, right? Those days are not happy days, right? Those are annoying days. If instead I spend that day writing some tests, right, I get, the time that I spend writing tests, I'll get back in not spending time debugging, and my blood pressure is lower on days I'm writing tests than it is on days when I'm fighting with the code to find when the problem is. So I have a happier life by embracing the pain of testing, right? Overall net. The other thing that I think is really important about having tests is this. Sometimes I want to make a change that will clean up my code, right? I want to, everywhere in my code, I called this variable x. And I really should have called it a sensible variable name that explained what the variable did, right? I want to make that change. But I'm worried that if I do that, I'll break it, right? And the code won't work anymore. So therefore, I don't make the change. So therefore, the code stays dirty. Writing tests allows us to clean up our code safe in the knowledge that I can verify that it's still right by running my automated test suite, right? So I'm more likely to make changes that improve the code. Martin Fowler calls this testing allows you to refactor with confidence, right? And I think that that's really, really important. It's worth remembering about different kinds of, we recommend what we call unit testing, right? People often use the phrase unit testing to refer to all automated testing. That's not correct. Unit testing is testing individual little subroutines, right? Testing at the level of, I've got a function, and for some times when I invoke that function, I can calculate what the outputs of that function should be. And then I'm going to say that when I call the function with these inputs, that should be the output, right? That's what we do in a unit test. And the reason that's much more valuable than other kinds of testing is as follows. When one of those tests later fails, which test fails in your test suite narrows down where in the code base the problem is, reducing the amount of time you spend investigating where the issue is. So unit tests not only tell you that the code is wrong, they tell you where the code is wrong. Other forms of testing don't. However, most of the time you pick up some code from somebody else. You just joined a lab, and the PhD student before hadn't come to this course. They won't have written any tests, and to actually write unit tests would take too long. You need to get the code onto test at all, right? Any kind of testing is more valuable than no tests. So don't be afraid to write a regression test. And a regression test is simply, I run the code, write down what it said, save that file to disk, and then I write a test that just says, is the output today the same as the output was yesterday? That's what we call a regression test. So to within some epsilon, possibly, if it's a floating point code, and there's a massive debate as to what epsilon is it giving the same answer as it was yesterday? Right? That at least gets the code onto test at all and is massively valuable. Unit tests are so much more powerful, but a regression test is is often enough to get you started. Another useful thing to do is an overall functional test. Sometimes you're writing some big analysis, and for a subclass of problem, the overall problem has an analytical solution, right? You can test that the overall assemblage of your code gives you the overall analytical solution in that particular case, right? And that's more powerful than a regression test, because a regression test only tells you that the code is as wrong as it was yesterday. It doesn't tell you that it's right. So in order of preference, regression test, those kind of functional tests on analytical solutions, then unit tests. Unit tests being most preferred. All the way up of order of preference, in reverse order of preference. But anything is better than nothing, right? Some jargon. So if I write a function with I write a function called add. Def add of A and B, colon, return A plus B. And I want to write a unit test for that. So I will write assert add of 1 and 2 is 3. This is called the fixture. It's the input data, the particular input data you choose. This is called the expected output. And this, the result of calling the function with that particular input data, is called the actual. So actual expected fixture. Notice that it is not possible to test for all possible inputs for this function, because there are an infinite number of those. All right? So we have to ask, how do we decide which particular sets of inputs to use? Right? What is a reasonable set of choices? We're not going to get infinite coverage of all possible invocations of the function. Coverage is the proportion of possible uses of the code that your test has done. Right? So different coverage measures. Right? Obviously, the fictional imagined perfect one would be for all possible values of all possible inputs. Right? Have we got 100% test coverage of that? Certainly not. There's a simpler one, which is just defined by have we touched every line in the code? at least once. We call that C0. We want to try and get some tests to get that number up. There's another one where if I've got an if statement here, so it could have gone that way, and I've got an if statement here, and it could have gone that way and that way, I can write one test that hits this branch, one test that hits this branch, one test that hits this branch, and one test that hits this branch, and get full coverage on the line-by-line coverage, but not have done all 4 of those combinatoric potential things. So there are higher coverage measures that try to cover that branch-wise coverage measurement as well. So coverage is the word for what fraction of the code has been, under some measure, have you hit with your tests. So how do we decide which, yes?
Just a quick question. In terms of readability, do you add all the tests within the code itself?
We'll come to that.
Okay.
In terms of how to decide which inputs and outputs to use. Okay, let's use a graphical example to think together about the question of which sets of inputs and outputs to use, and then I'll rant about some opinions. So here's an example of a research project to discover the changes in the field patterns of Saskatchewan in Canada. Anyone Canadian? Saskatchewan, Saskatoon for the province? No? Anyway, sorry, Canadians on the internet, apologies for pronouncing your place names wrong. Hi, Greg. The question we want to know, for the computer problem we want to know is, given 2 sets of fields, and fields in this province in Canada are all perfect rectangles, so it's nice and easy to do this. So given 2 sets of top left and bottom right coordinates for some rectangles, what is the area of overlap? Right, that's the problem we want to solve. So given this problem, one field, so this might be the photograph taken on January 2000, year 2000. This one might be the photograph taken in the year 2010. What is the area of overlap of those 2 fields, where one of them has its bottom left corner at 1,1, its top right corner at 4,4, one of them has it at 2,2, one of them has it at 3,3. The overlap here is 1 unit of area, right? 1 hectare or whatever, okay? So we want to write a computer program to given the top left and bottom right corners of each of the 2 rectangles, what is the overall area of overlap? That's the problem we're going to look at as an example to think about how to write tests for it. Here is a test that I should write. But it's not very different from the previous one. Here, the blue one is still inside the orange one, overall overlap. So what I want you to do now, talk to your partner, grab a piece of paper, draw. So pick someone sitting near you, right? Talk to them. Draw out, you don't need to write the code, draw out what you think would be some sensible test cases to address in this context, besides this one of a blue rectangle inside an orange rectangle. They're completely separated, overlap 0. Yeah? What else?
Just an edge. Just an edge.
Just an edge. And just a corner. Yep. Yep, so. Yep.
Blue bigger than orange. So
yep, so all of these through the blue into orange symmetrical reflection.
No area.
Yes, good. Bottom left and top right the same as each other.
Partial overlap.
Yep. Partial overlap through one side, partial overlap through the other side, partial overlap all across that way.
Different orientations of the same area?
How's that?
So if one's along way
Yeah.
and one's
So indeed, there's some interesting test cases to do with. In this case, I've only got integer corners, but if I had something like that, maybe I need to check this kind of extreme cases where this one is 1,000,000 units wide and this one is 1 unit wide, right? Maybe I've got some loss of precision problems I need to look at. Yes, exactly. So what we've seen is people have got this quite intuitively with this geometrical example. We need to use the same intuitions here when we think about examples that don't have a geometrical intuition. And what we're looking at is equivalence classes. So think about different equivalence classes, and then look at the boundary points where those equivalence classes transition. Yeah? Look at degenerate cases, like the individual point. Look at extreme cases. Yeah? There's one other kind of thing we should also be looking at, which is where cases where the data comes in wrong. So where I've got one square and one thing that the program doesn't know how to handle, right? So a string or data in the wrong format, right? So if we've got those sets of things, so the different equivalence classes, the boundary points, the degenerate cases, the extreme cases, the empty cases, and the cases where the data comes in wrong, that's most of what you need to think about. The other point that we were talking about while someone was doing it is we want to avoid symmetrical cases. So consider this is the first example we had was one perfect square exactly centered inside another perfect square. If I made a mistake where I'd accidentally typed x in one of the places where I should have typed y, that bug would not be caught by that test because the x value and the y value were the same, so therefore it would have come out right. So I should avoid symmetry. I often find myself choosing numbers that are different primes when I'm writing tests. So I'll use 3, 5, 7, and so on as my numbers. So it's less likely that I get coincidental correctnesses under those circumstances. Yes?
Can you mention again the symmetrical case?
Yeah, so imagine I was writing my code, right? And I typed in I'm going to do it now and type in my code that solves this problem. Imagine I just accidentally in one place where I should have typed in x1, typed in y1, just as a typo while I was coding. Because in this case, the value of x1 is the same as the value of y1 as a number. They're both 1. The test would still pass even in that case where I'd typed it in wrong. Okay, so here are my solutions. So let's actually do this now. So here's some code that implements the overlap problem. And I've run the simple symmetrical case, and my overlap thing is given 1, which it should have done, so I reckon the code is right. Okay, this code looks plausible. It says, where is the overlap left? It is, here is the left-hand side of that one, here is the left-hand side of that one. Whichever is the maximum of the two left-hand sides is the left-hand side of the overlap area. Repeat for each of the 4 things, take the differences and multiply. Sounds like a plausible solution. Okay? If you see the mistake, don't shout it out now. We're going to let the tests find it. This is how we write a test. We say assert. This is the Python way. We say assert, and then we write down the call of the function with our fixture and the expected. And nothing happens indicating the code is correct. If the test fails, we get an assertion error thrown. And this one, which should be correct, so the bottom left is at one rectangle is at 1144. The other one is at 4.5, 4.5, 5, 5. So we've got a rectangle there and a small rectangle over there. That should be 0 overlap. But our algorithm has printed 0.25. Someone's just seen why.
I think it's negative numbers?
Yes, that's correct. So what's happened is overlap width and overlap height have both come out as minus 0.5. So when I multiply those two together, I get plus. So the correct solution needs to be overlap height is whichever is the greater of 0 and the thing we had before, right? So the point is that we needed a wide enough test coverage, including this example, in order to hit that problem in the original plausible-looking code. Okay, and this is the approach that testing. This is the approach that unit testing takes. Yeah, we're trying to get enough different examples that we hope will hit things like that. Notice that after writing the new code, I not only rerun the test that I just found was wrong, but also rerun all my other tests as well to check that in fixing that thing, I didn't break one of the other cases. Okay? The jargon term for that's a fallout bug. So you fix one thing and another bug occurs as fallout. Now, the other category I mentioned of kind of tests we should do is testing the data, is testing that it gives a sensible error message when the data comes in incorrectly formatted. Because what you don't want it to do is I say, what is the area of overlap between this field in Saskatchewan and a squirrel? And the answer is 2, right? What the answer should be, I'm sorry, you've just given me a squirrel. Why the heck have you given me a squirrel, right? Or in computer terms, that means throwing an exception, right? We want it to say unexpected squirrel error, right? And so we need a way to write tests such that we can say the answer is not equal 2, but equal crash, right? And we don't yet know how in Python to phrase assert crash, right? In order to phrase assert crash, I'm going to show you how to use a testing framework, which then makes that available. And then we can do what we call negative tests. And negative tests are the tests that when it goes wrong in the expected way. And to the disappointment of everyone, I've decided not to do a break because I want to get to the end of this testing material. I'm not going to have time to get to the numpy stuff, sorry. But so I hope everyone's concentration power is enough to carry on for another 35 minutes or so. Is that all right? Yeah? I mean, I'm going to anyway. But so let's look at the PyTest, which is a standard Python testing framework. I just scrolled past in the notes a list of testing frameworks for different languages. So whatever language you're using, you should use some testing framework. What does a testing framework do? Right. What it does is, well, first of all, it provides you with some more scaffolding to write different kinds of tests. So in this case, we can use this raises thing, which we can import from PyTest, and then we can write with raises the exception we want to get, and then the code that should generate the exception. And if this passes clean, because that does raise the error. And if this didn't raise the error, this test would fail, right? So it's kind of backwards in your mind. So that's the raises thing that does that. But the main power of testing frameworks like PyTest is this. And this answers the question that was asked before about where to put your tests. Okay? Because what PyTest does is so here's my overlap function. I'm just writing out my overlap function in a nice little Python package, laid out in the way I described earlier with laid out in the way I described earlier with that structure. But I've also put in a module here called test_overlap.py. And in that function, in that file, I've made a few functions called, and each function is called test_name_of_test. And what PyTest does is it automatically looks through your code base from the point where you invoke that command at the terminal. So I type in py.test at the terminal. And from that point where I type in the terminal, it recurses down the directory structure, looking for files called test_something, which have functions called test_something in them. And each of those functions called test_something, it treats as a test. And it runs those separately. And when it runs, you get a little dot for each test that passes, and a little F for each test that fails. And where a test fails, it prints out what the actual and expected were, so you can diagnose it. So that's how you should lay your tests out. The tests for each class are in a file called test_nameofclass.py, and each of the tests is an individual function. Other features that it has that are rather useful is then because you've named your tests, by giving each test putting each test in a function, you've named your test with the name of that function, you can then filter out to only include tests that include or do not include certain words in the name of that function, allowing you, for example, where you have a test suite which takes quite a long time to run, to only run a certain subset of those tests. So I might, while I'm hacking away to get a test to work, only just keep running the particular test that was failing, and then when I'm happy, run it without the filtering switch, pytest -k, and then the text you're looking for is the switch that does it, to then run the full test suite and recheck everything. Okay, so I would always use one of these test frameworks. Let me talk about a really thorny problem in testing in numerical code, which is that testing with floating points. So because lots of the stuff we do involves floating point math, and so therefore often our code is only right to within the precision of that number in the computer. So I need a fluent way to write tests that do that. And PyTest provides the approx function. And the word approx and then a number generates a kind of object which evaluates true under the equals operator to anything that is within. So it's done operator overloading on the equals operator, for those who know what operator overloading is. What it means to be equal to something for these approx objects is not the same mathematical operation as the usual equality. It's equal to within one part in so-and-so. And so I write assert 0.7 is approximately equal to equals approx this. Yeah? The default for approx is relative tolerance of 10 to the -6. I can specify different tolerances with rel equals and abs equals as keyword parameters to change the absolute and relative tolerances. Relative tolerance is one part in, absolute tolerance is just a fixed difference. Yeah? Of course, the art is deciding what these epsilons should be. And that is a active area of research and controversy. Nobody's quite sure of the best way to decide what the epsilon should be. In principle, if you set it too precise, sometimes your tests will fail as a result of floating point vagaries when they shouldn't. That will waste time. If you set it too high, tests will pass that shouldn't pass. I'm not so concerned about it theoretically because remember, we're not trying to prove our code correct. We've got all of our clever computer science friends who are interested in code proving who want to do that. That's not what we're trying to do. We're just trying to increase the likelihood that we discover problems, right? So I'm not too concerned that I don't have a strong theoretical grounding to decide what the tolerances should be. In NumPy, there's a useful tool called assert all close, which you can insert from NumPy to take a pair of NumPy vectors and assert that each element of those is close to the other. So that's the best thing to do when you need to compare long vectors of floating points together. And again, that takes relative inputs. I'm going to look at another example. So if you want to try and run this example outside the classroom as a little bit of work for yourselves to practice your learning, you can. I'm going to give some answers now, but it's a good one to do of your own. So normally we would, if I'm running the full lecture course, we break and everyone does this in pairs and then we come back together again. But there was not going to be time today to do this. So this is an example involving one-dimensional diffusion. So we've got a corridor of some kind, and things are allowed to be at integer positions along the corridor. We're just going to say integer positions to make the example simple. So we've got a 1D discrete axis, and agents which are going to be able to move around in that axis, and they don't like to be where other things are. So you might want to think of these as particles in a gas, or people in a street, or animals in a habitat. It doesn't really matter. It's anything that wants to be isolated. And we have some unhappiness function or energy function, which shows the extent to which things have got neighbors that they don't want to have. Yeah? So if I'm by myself, I have energy 0. If I'm with one neighbor in the same place as me, I have energy 1. If I have two neighbors in the same place as me, I have energy 2. Yeah? So if there are 3 people in a site, what is the energy due to that site? Six. That's right. Each person has 2 neighbors. They're each unhappy 2. Therefore, the overall unhappiness is 6 from that one site. So this is the formula for the overall unhappiness of the structure. Okay? This is not a course on modeling of diffusion of animals in ecosystems or people in streets or particles in gas tubes. So I'm not going to spend any more time on that. This is just an equation that we're going to try to write some tests for. Yeah? So I want to write my model code in one file and my test code in another file. And note that in my test code, I need to import my model code in order that it can access the function in order to assert against it. And then I run my tests. And at the moment, I'm on Windows, so I need to change bash to CMD there. I've got one test which doesn't do anything, so of course it passes. So I'll write my first test. And that test failed because it should have returned 6, and instead it returned none because I haven't written any code yet. Right? And now I can start writing my code into the energy function. Still failed. Wasn't expecting that to fail. I was expecting it to pass. Can multiply sequence of non-int by type of list. I typed density there, and I should have typed val. And now it passes. Note, that's how I'm hacking. I write my test first, and then I write my code. And in order to invoke my code while I'm coding, I do it through running the tests. I didn't open a Python shell and call energy manually with some inputs of mine. Right? This way, the tests start writing themselves. Because our previous way of working would have been to try calling energy with a few inputs in the notebook. Right? That's not good, because I'm not storing, if I do it this way, each time I invoke it, what I actually do is write another little test, right, with the inputs that I want to use, and I'm hacking directly against those tests while I'm developing. Yeah, and when I think of a new thing, I need to check that, I'll write a test for it, and then run with py.test. So only right at the end of the project do I actually write my command line interface with argparse and call it. Most of the time I'm coding, the only way I'm interacting with the code that I'm writing is by invoking my test runner. That's called test-driven development. We write the tests first and then the code. And we write the tests and code alongside each other. So here is a richer solution for the code and tests. Note what I've actually done in the proper solution has no for loops. Because NumPy arrays, the star operator for NumPy arrays does element by element multiplication. So what I actually do is turn my input into a NumPy array, if it's not one already, and then just do density times density minus 1. This is an element by element subtract, and this is an element by element multiply. And in my tests, let's look at the tests we've got. So we've got some negative tests. It should raise an error if the integer if the density it gets is not an integer. It should raise an error if the density it gets is a negative number. It should raise an error if the density it gets is not a 1D vector. Okay, so I'm asserting that I'm getting the kind of data I'm expecting. I've got a bunch of different test cases as fixtures to try, all of which should have 0 energy. And I'm looping over my different set of fixtures in a for loop. So I'm doing many tests in one there, and that's quite a nice way of setting up tests. One thing you can even do is create what's called a fixture file. You can create yourself a JSON file or a YAML file that contains all of your inputs and the expected outputs, load in that as a data structure just by doing JSON.load or YAML.load, and then loop over that. And then when you want to add new tests, you're just changing them in that data file, making your test suite data-driven rather than changing the code all the time. I haven't bothered with that here. Here's an interesting test that I've written. Actually, I didn't write this. My colleague wrote these lecture notes. But we've asserted that the derivative of the function has a certain functional form. What we've done here is we've said we're going to generate random inputs, completely random inputs. We don't know what the answers are going to be in those cases, but we know something about them. We know that if I add one more particle to a particular site, the energy should go up by the number of people who were already there, times 2, because each of the people already there has now got one new neighbor, the extra person that arrived, and that person has got the number of people already there as neighbors. Yeah? And in fact, mathematically, that's because the derivative of n squared is 2n. So this can be a very useful way of writing tests where I don't have a functional form for what the function's output should be for anything except the most boring sets of inputs, but I do know some other derived properties of that function. In this case, I knew its derivative. Right? I mean, in this case, I could have actually tested the formula because the formula is pretty simple, right? But in some circumstances, I won't. You will be trying to code tests or functions that you don't know whether you've coded it right, but you'll know some properties of that function. You'll know that the answers should be symmetric under interchange of some of the parameters. You'll know that if one of the parameters is 0, then the answer should be equal to one of the other ones because a particular term isn't operating, stuff like that. You can test those properties of the function as properties where all the other inputs come from random samples. So it's another way of introducing potential tests. Just to note that here I can run my test with --cov. Here, sorry, I can run my test with --cov and get a little HTML report that shows what percentage of the lines of code my tests have hit. So this is the C0 measure that I was speaking of earlier. You know, the simple per line of code, has it been hit thing. So that's a useful thing to do to see whether, you know, what my code coverage is. Why is it jumping to that one? I don't necessarily want to look at the comparison. Here we are. Good. Okay. So let's look at this. Actually, let's look at UCL. Go on, let's look at all the tests in UCL. All right, let's look at this one. Go on, fine. So build history. There we go. So here's a live project that we're working on in the Institute at the moment. And we are looking at our Travis setup for this project. And what Travis is a tool which every time I commit the changes to version control, every time I do a git push, it automatically runs my tests for me. So on a server, it goes py.test on the server, and if any tests fail, it will email me. Why is this useful? So if my tests take quite a long time to run, that's useful. If I'm in a habit of forgetting to run my tests and just committing anyway, that's useful, or if my colleagues are. But more importantly, I want to test that the code works on several different versions of, in this case, R. Downloading all those different versions of R on my laptop would be a pain, right? But if I'm trying to write a library for other people to use, I want that to be the case. I can write my test code. So let's find this code in GitHub. So how do I set Travis up? In my repository on GitHub, I create a .travis.yaml file, which amongst other things, in this case we are only testing on one version of R, so that wasn't a great example to say. But anyway, never mind. And I can set which the parameters of what libraries I want to be installed, what tests I want to run, and so on when I want to invoke the code. So here, oh look, we've got a Slack plugin. So it's actually every time it fails, it's going to put a little message in the Turing Institute Slack channel saying that the tests have failed. Okay, so this is how you do testing on, you can use this to do, I'll show you another example if I can log in correctly. Yeah, it's not going to work. All right, so I've got some projects where I'm running with several Windows, Mac, and Linux, several different versions of different operating systems, and several different versions of the C compiler and the C++ compiler and so on, and checking that they're combinatory explosion of all those different circumstances all the tests pass in, right? Because don't know if you've ever noticed about code that works on your laptop and doesn't work on your mate's laptop, right? This is how you stop that problem from happening, okay? One other thing worth noting, you don't just have to use these tools like Travis to run tests. You can have pretty much anything happen automatically every time you commit to GitHub. So that's how my lecture notes work. So this is the Travis file for the repository for my lecture notes, which downloads those IPython those Jupyter notebooks and puts them through the thing that turns Jupyter notebooks into HTML and the thing that turns Jupyter notebooks into LaTeX and then PDF, and then uploads that to the website where the lecture notes go online. So that's how I automatically turn the Jupyter notebooks, where I do the development of the lecture notes, into the website for the lecture course. Why do I do that? Because almost every time I've ever read any kind of textbook on computing and tried to copy code out of the textbook into my thing, it doesn't work. At least this way, I know that all of the examples in my lecture notes do work because they're running code, right? And if it doesn't, it's supposed to be, actually it's not working properly at the moment, it's supposed to be that if any of the examples don't work and crash during this, it doesn't upload it, it doesn't do the upload of the updated lecture notes to the web. So there's other things you can use continuous integration for. And in particular, one of the things that it's really common to use it for is, remember when we talked about documentation earlier, you can have that Sphinx run, which turns your comments in your code into the HTML for the documentation to happen during your CI run and upload your documentation onto the website. So that's how we use. We use Travis to do automated testing. It's free for open source projects. You have to pay a small fee for private repositories. UCL pays for it for UCL people. If your institution doesn't, ask your institution to start paying for it. What else? So I think that's what I wanted to talk about on testing. Shall I do mocks? Yeah, it's probably worth doing mocks.
So just very quickly, so what was JSON?
Sorry, okay, so yes, so in the example there of the YAML of that config file, this config file for Travis is a YAML file, which is a text file that contains structured data. So here, this is a dictionary where each of the dictionary values is written there with a dash. So that's YAML. JSON is another similar file format that does basically the same thing. So it allows you to, it's a text format for describing things that are dictionaries and lists of dictionaries and dictionaries of lists. In JSON, you use curly brackets to start a dictionary and square brackets to start a list. All JSON files are also YAML, but YAML has this slightly cleaner, more readable syntax where you don't have to bother putting the curly brackets. So just writing something colon like this tells it that this is going to be a dictionary. So if I load this file into Python or R, what I get here is a dictionary whose first key is dist and whose first value is trust.
Okay, right. So YAML will be the preferred one for Python.
So I prefer YAML, yes. YAML is my favorite format for data where I don't care about performance, so I don't need to use a binary file format. I want to get a human readable file format, so I'll go for YAML, and I want structured data where I need to have non-tabular data, so to have lists of dictionaries and dictionaries of lists and that kind of thing. I'll use CSV if I just want tabular data. There's a section in the lecture notes on data file formats. It looks at Travis and it looks at JSON and YAML and XML and CSV and that kind of thing.
Sorry, so all of these are kind of keywords that Travis recognizes.
Correct.
To
Yes.
test for.
So the way Travis configures its server that's going to build is by passing a file like this that specifies here are the packages. So this is basically what to apt get. So it runs Linux on the server, so it needs to know what to apt get. So it does that. Yeah, and here is the list of things to pip install, and then what to run, and then after a success, what to do. So I just want to talk about one other useful tool for writing tests, which is this library in standard Python library called mock, which allows you to write tests in the following circumstance. Write tests in the following circumstance, where you have to, your program interacts with other parts of the program. In order to make your test work, you'd have to set up lots of other classes and objects for your code to interact with before you could write the test. That can be difficult. So instead, what you want to do is simply create a mock object, a dummy object, which will play back certain answers when asked. So here I've created an object called function, which, when I call it, with any kind of input, it's going to give the answer 2. Why is that more useful than just writing a function called def function return 2? Because it records what it's been called with. So I can then assert at the end of my test that here's my section of the program that's under test. Here's the other section of the program that I don't want to be bothered with yet, but I want to assert that they're interacting with each other in the way intended. So I can assert that my mock for the rest of the program has been called in the way I want it to. So here's an example. So imagine I've written some code which is going to get me a Google map for a particular place. Okay, so there's London as a Google map downloaded thing, and this library basically just takes as parameters the latitude and longitude, generates the kind of URL structure that Google Maps wants, downloads that from the internet, and then returns the object as a bitmap image. Yeah? I want to check that that code is correctly generating that URL. But I do not want my tests to fail if the computer that I tests are running on has lost its connection to the internet. I might want to work on the train. So I'll replace the requests library here, which is the Python library that does downloading resources from the internet, with a mock that instead of doing that, records the URL that it's recalled with, and I can assert that that URL is the URL I expected. So here's how I do that. From unit test.mock import patch. With patching, the get function in the requests library, replacing that temporarily with a mock for as long as this with Python Context Manager is in play, run my code, and then in this case, I'm printing out what my mock was called with. I could write some assertions on what the thing was called with, and that would assert that it had been called in the way I wanted. So here's my test. So with patch, request.get as mock.get, column map, this is my unit test, and the assertion line is mock.get.assert called with, and then the set of parameters I require that it would be called with. And then I've decoupled my tests from having a working internet, because I've mocked out the part of the code base that does the interacting with the internet and replaced that with a mock. Also useful for testing functions that call other functions, because I can make the function that I'm passing be a mock, then assert that it's called in the ways I wanted. So that's a useful thing to do. Right, 12:54. I haven't got time to cover the NumPy stuff. Let's take the last few minutes to do questions on testing and on anything else that's come up during the morning. Yes.
Yeah, I can see how test-driven development is invaluable when it comes to creating packages and software. What I was wondering is when it comes to taking a package and then applying it to analyze the data.
Yeah.
Where does testing slot in there now?
Right. So the real question is, where does usage end and tool writing and usage of a tool end and tool creation begin? I have never seen in particular thinking about the data science context, a analysis where I didn't need to write some functions to do the cleanup stage, right? And I will want to assert that for known kinds of messiness in the data, my parser is doing the things I expect. I almost always want to do some kind of pipeline, right? And I might want to check that for data. For another good example is if I've got some synthetic data, I want to check that my analysis is giving the answers expected on the synthetic data, right? I can do that automatically for my synthetic data, and then I can write tests to do that with assertions, rather than just normally we do this all the time without thinking. We eyeball our results to check that they're the ones we wanted, right? Instead of eyeballing the results, I'm going to write an assertion. Right? And then that assertion can sit in an automated test case. And then when somebody updates the data set, or when somebody updates one of the libraries that I'm invoking to do the analysis, I can automatically rerun and check that nothing's been destabilized. Right? Because here's why I like continuous integration. Have you ever been in a situation where you submit a paper and 6 months later the referees finally get back to you and say, That's great. I just think you need one more figure to show this. And you think, super, I'll just get my code working again and add that one more figure. Oh no, the code totally doesn't work anymore because something's changed in the last 6 months. If I'm using CI, and I've told Travis to run my analysis every day and email me if the analysis doesn't work anymore, then on the day when that particular library gets updated that stops the results working anymore, or the data set that let's say I've done my analysis the way that I like to do, where I'm automatically downloading the data set from its data source by downloading it off the internet. And on the day when they change the data format, right, Travis emails me and says, your analysis is not working anymore. And then I don't have that horrible headache where the just one more graph thing turns into a massive exercise of trying to get all that scaffolding that I had that made that analysis possible on that day up and running again. Yeah?
Can we make Travis run every day without commit triggering?
Yes. Yes, you can trigger your CI tools to run on a cron structure, so every so often, or on push. You can also just cron to put a fake push in or something. But yeah, there's a.
If you had a function, say, that was kind of stochastic in some way.
Yes.
Do you set the random seed?
So there's a few different. So this is one of my favorite topics: is how do I do unit testing for Monte Carlo, right? Which is really, really interesting. Locking down the seed is what we normally do. Again, if there are overall, if there are analytics I can test that it's within some epsilon, right? I will get some spontaneous failures there, right? Where one time in n is going to be outside my range. One thing that we came across that was really interesting was testing for Monte Carlo in parallel computing, where we had to make it so that the answer we got was the same, independent of the number of parallel processors we used. And the reason that was complicated was because you want to make sure that even if you lock down the, if you lock down the seed, but the different processes are getting different elements from that feed. So what we had to do was mock out our random number generator in such a way that we pre-recorded the list and made sure that whichever step of the calculation was happening, it kind of knew to pull out the bit from the thing independent of which processor it happened on. It was very complicated to get parallel Monte Carlo code to give consistent answers in unit tests independent of the thing. But in general, the best thing to do is just lock down the seed and then assert within an epsilon on whatever whatever results you want. But in those circumstances, what you should also be trying to do is focus on unit testing, because even though the overall calculations are Monte Carlo, individual specific bits, you can still assert that with these inputs, these are the outputs. Any more for any more? Okay. Oh, question.
Can you show the link again?
Yes. So no, because my computer's run out of power. That was good timing. GitHub -pages.ucl.ac.uk/rsd-engineering course. And the thing I took the slides from about the different failure modes in research software engineering at the beginning, that talk, is the talk that I give called The Craft Person and the Scholar, and the URL for that is just bit.ly/RSE talk 17. So this is the lecture course, and this is sort of my talk that I give in various places. Hope that was useful. I'm done. Bye.